All right, so I didn't grade the homeworks yet, so I didn't get a chance. I'm still kind of looking for a paper for this week, so I'll probably have that posted before 5 today, the next one. So let's see. So I'm gonna get to this. So I'm just gonna go through the notes. Any questions on anything, you guys? All right. So all right, so we're kind of here. So I wanted to just let's see, we did that business. All right, so this is what I wanted to do first, this thing. So if you have so we have this NL squared law, like the average square of the end-to-end distance of the chain is n times the kind of the absolute value of the step squared. So I'm going to do that a little bit. So that gives you this, let's see, that's good. That gives you this idea that you have like, so you have like r squared to the 1/2 would be kind of size. So that's basically the distance between angles on average. It's looked at as the size of the chain. I mean, it isn't really a size. Again, it's really, you have a probability of some end-to-end distance versus size, and that's the standard deviation, which is like something like that of a distribution of sizes and truncates at the contour length. So anyways, but it's used as a size because nothing better, because the thing looks kind of like a cloud. It's like you say, what's the size of a cloud? So you have a little problem with that. Okay, so that's going to be into the 1/2 of L for this will be the Kuhn step. Right. So you can talk about density of things, right? So you say like if you have a mass for a 3D object, you have a mass, and that goes with kind of how many things are in it. Say you have a wall made of bricks, and like how many bricks are in the wall gives you the mass of the wall, or a 3D wall. Right? So then you say the size of the thing would be kind of, like you want to talk about some kind of R thing, would be into the 1/3. Like you have like one side of it, you have mass, kind of the side is going to be only 1/3. So then if you want to know the density of that, you have the mass over into the 1/3 cubed, which gives you like kind of 1. So the density is fixed. The prefactor of this is the density, like rho 0. So you have density is density, and it doesn't change with how big the wall is. Right, which isn't true of polymers and other things like polymers. Okay, so that's kind of an odd thing. So you can say, well, all right, so we have that for 3D. Let's talk about this thing. So the polymer, then we have the mass of the polymers in K, and the volume of it's going to be this R cubed. So it's going to be, so the volume is going to be scale. So this squiggly means scales with, it means there's some prefactor that I'm ignoring because sometimes you don't know what it is. That thing cubed, right? Which that's going to be into the 3/2. So then you have this weird thing that the density is going to scale with the mass to the -1/2. Right? It's different than the density is the density. That means if you have a small polymer chain, it's much denser. It's going to be a lot denser than a big polymer chain. That's a little bit odd. right? So then you could take that to the extremes. You could say, if you had like a rod, you have a nanotube, a carbon nanotube, it's a rod, supposed to be a rod. And then, so you'd say that the size of that, so that this length, the size of an L, which we're talking about is R, goes with N. If you want to make it up of N bricks, and it's just N is the size of it. And then let's see, the mass of it's going to scale with N. Also, they'd say, well, what's the volume? Well, if you take that object and kind of like spin it in space, this is what we're talking about, is like randomly arranged. So then you'd have a sphere, right? Some kind of sphere made up of rods that are spun around, right? It would have this, it would have a volume of R cubed, right? Which would be N cubed. And then we'd have a mass of N still. So you'd say the density that spun around carbon nanotube is going to be some constant prefactor than 1/n squared. So that's even worse. Like that's a terrible situation. In other words, if you have a small nanotube, it doesn't take up much volume. If you have large nanotubes, which are the idea, like micron size and then nano size diameter, then that's going to be a huge drop in density. Density goes zero, right? So that's kind of interesting, you know. Then you want to make a composite. This might, I found a paper on this. It might be a good one to do on this, but so basically, you want to make a composite of that. You have an extruder, you throw in some polymer, and then you throw in a bunch of nanotubes. So how many nanotubes can you put in before you get this problem that the nanotubes like hit each other and then they do this? Like they just cluster into a clump of nanotubes. I mean, the idea of making a composite of this is that you're going to have like independent nanotubes, and then the modulus should, because the strength of this nanotube is huge. The carbon double bond is like a huge strength, right? So you could, conceptually, you could get an enormous modulus out of a composite with just a small amount of nanotube. The problem is, once you get to this kind of density number, say your concentration equals that density, this density, which is going as 1/n squared, then all of a sudden they start touching, and once they touch, well, the nanotube and nanotube are the same, and the nanotube and polymer are different, right? So basically, the nanotubes generally want to be with nanotubes. They want to cluster together, like there's some kind of affinity. The aromatics in it have this kind of ring current, and there's extra electrons. There's a fraction that leads to like kind of a polarity within the ring that makes the rings want to stack, like the nanotube rings want to stack together. So you have a natural attraction to each other due to this ring current. So I mean, they're made of aromatic rings. So anyway, so basically they will just stack together and make a clump that's useless. In other words, you get a micron-sized clump of carbon versus a nano-sized super strong fiber. That chunk of carbon is just like adding coal to the plastic. It's not going to do anything except make it break easier. You get flaws on the surface. Anyway, so that's one issue. Like this kind of, so this concentration is called like the overlap concentration. That's like the magic concentration. And for nanotubes, it's going to be a fraction of a percent, like maybe 0.1%, like a very small fraction. For polymers, it's going to be about 1 to 2% for normal 100,000 molecular weight polymer. Right. So this overlap concentration is where you're going to see things happen. Like I showed you a plot of like viscosity, solution viscosity. So that's going to be the viscosity of the solution minus the solvent, and then normalized by the solvent. And that has when that has a value of 1, generally that's at a concentration of about 1% of polymer. And then you see like it'll take off because the chains will start to entangle. It'll go up to the power of about 3. This is the power 1 when you add polymer to a solution. Right, so that's a C star. That's like the magic place where the polymers start to overlap with each other. Right, so, sorry, this can be kind of generalized, so you talk about, so you can talk about the, so if you look at, scattering, there's a signature of this in scattering, kind of say branch polymer, this could be a silica aggregate, or it could be some kind of branch nanostructure. So in scattering, like I said before, this is intensity is kind of the mass. This is 1 over the size, this Q. So you have mass versus size. So the slope is this dimension of the object. And I said that the dimension is 2 for a polymer coil. So it's not 3D. That's why it has this density thing. Basically, that's kind of the density scaling factor, like the factor that's going to influence density. You can we can write that here. Oops, did that do that? Yeah. So we have R goes with n to the, so R to this dimension gives you n, right? So here, if R goes with n to the 1/2 times LK, this is NK, then this dimension is 2. So polymer, this is called the mass fractal dimension, is 2. And if you do like that, the density is going to be the mass over the size, which is R to the size is going to be n to the 1 by df. Then we're going to cube it, so 3 by df, and then subtract 1, so you have 3 by df minus 1 is minus 2 by 2. That would be 1 by 2, so 1 by df, that you end up with, right? So the density is going to go with the mass, so the 1 by df, like a general rule, and then you can plug in that the df for rod is, oh, well, that didn't work. Let's see, I did this wrong. It's going to be the other way around, right? So it's going to be, oops, sorry about that, 2 by 2 minus 3 by, yeah, that's what the power is here at n, which, and let's see, or 1 minus 3 over df. Let's see, I mess this up. N is 1 minus 3 by df. Right, so if you put in 2 here, you get 1 minus, if you put in 1 for a rod, you get 1 minus 3 is minus 2. If you put in a 3D, you get 1 minus 1, you get 0. So that means it's a constant density for 3D. You put in 2, so you get the right answer. So this df that we're talking about that you can get in the scattering, the only thing it determines is the density. So it's just saying what's the density, how does density scale with size? So as you go, so Q is 1 over size, so at low Q you're seeing, this would be like a scattering, like neutrons, X-rays, or light. The intensity you get out, and then that's proportional to the concentration, so you normalize by concentration. And then as you go up in size, you see this, the change in the mass goes with this dimension, this fractal dimension thing. So basically, this is just telling you how the density changes with size. Right? Yeah. Because it's you start over here. So we have the size, so the size for the df gives you the mass. Okay, so the size goes with n to the 1 by df, and the volume is going to go with n to the 3 by df. Okay, so you're going to have the mass, which is n to the 1, divided by n to the 3 by df gives you n to the 1 minus 3 by df. That's kind of your density scaling with mass. So that it tells you that, okay, so you're getting this idea, like, yeah, oh, I can tell the difference between a rod and a coil and a 3D brick, whatever, right? But you can't. All you're telling is the difference in the density between a rod and a coil. So you can't actually reproduce the structure knowing that one number, because it's other objects, with the exception of a 3D object and this, there's many things in between that have a number between df equals 1, df equals 3. And the simplest one is that a random walk coil has a dimension of 2, and another 2-dimensional object is like a plate. Right, so if you have like a plate of spaghetti, see, I always thought this was kind of interesting, but no one else seems to be interested in this. But anyway, you have a plate with spaghetti. In terms of fractal dimension, you can't tell the difference between the plate and the spaghetti. So you'd be eating the plate, you know, if you like spaghetti, or you might like plates, but anyway, so. Okay, so there's a problem with this. The F number is not telling you like exactly what the thing is. It's only telling you the density. Right, so it's something to keep in mind. Like, so people, so a lot of times in biology, this comes up. People are looking at, like I mentioned, there's proteins are normally like folded and collapsed down into an active agent, like insulin collapses down into a nano-sized thing, even though it's kind of almost micron size in length. And that functional unit has sites where it can do whatever glucose hydrolysis, whatever it does, right? So, and if it's unfolded, then you die, you know, because it won't work. It's just the same material exactly, but if this topology of it really matters. So biologists would go in and do scattering and go, oh, it's got a 2-dimension, so it's a random walk, right? But there's a problem with that if you take an egg and just whip it, right, and then it turns into like whatever you make foam stuff to eat, get the name of it, but anyway, you're denaturing the protein. So the egg, beginning wise, is kind of folded proteins, and you unfold it. It's true, you unfold it, and if you did X-ray on it, you get a power 2, but it's not unfolded. The natural way proteins fold, when they're just ripped apart with a fork, they form beta sheets. So it's forming sheets, which are 2-dimensional. So you're saying it's unfolded, but it isn't, right? So it's a problem with, but in biology, people say, oh, this is evidence that I've unfolded the protein, and it isn't. It means you just made a misfolded protein. The beta sheet forms a natural misfolded state. They would have the same dimensional scaling here. Yeah.
That lower density is this thing is unfolded, or are they related? Like, can we interpret it folded or unfolded by seeing the density?
No, I mean, all right. No, I mean, if it's sheets that are randomly arranged in space, no, you can't, because they would have the same density dependence on the mass.
Yeah.
So in order to do this, you need to have different mass whatevers, and then compare, and then plot the density versus the mass. And then it would have a power law. So you do log density, log mass, do a power law slope, and the slope would be 1 minus 3 by df. The df would tell you the density scaling with mass, right? So it's not telling you anything about exactly what the thing is. You can tell it's not a rod. You can tell it's not a 3D object. And then within the realm, so like if you have a randomly branched polymer that's Gaussian, it's got a dimension of 2.5. But you can't exactly say that. All right, so anyway, there's a lot of caveats to this. So you have to kind of keep in mind that this dimension doesn't tell you like the whole story of what's going on. Right. So you can get that dimension, you can get the overall size, get the Kuhn size. In this case, they have solid surfaces, they have a steep slope. With polymer, this would be a power 1 here. And then as you add the concentration to it, you reach this point where you have overlap between the coils, or between the particles, right? And then if you reduce this by concentration, there's a reduction beyond the constant. So the concentration drives this up. So if you reduce linearly, so if you divide by concentration, you find out that it's not giving you what you expect to get. It's less, because at some point, instead of seeing the size of this, you're seeing kind of you're seeing the smallest thing that you can identify here. So once they overlap, it can't be identified. Like this thing, this fleece is made up of fibers, right? So if you could see one individual fiber, it would be a chain of a certain size, right? But if you see this fleece, basically, what you can see if you zoom in with a microscope, the first thing you can see is when it has holes. Like, what are the holes? And that's kind of the correlation length between the chains. So this correlation length takes over the size that you observe, and you can't see anything bigger than that. Bigger than that, it's smeared out. So all you see is just solid. And solid 3D just has a constant intensity because the density is constant.
It doesn't have any scaling. It's just constant after that. And as the concentration goes up, those holes get smaller. So that kicks this Q's one over size, that kicks it to the right. And this just continues to go down. The rate at which that goes down with concentration tells you how the chains are interacting. Like it gives you the thermodynamics, like the free energy of interaction between the chains. So it can be measured. You can measure that, right? So that's kind of a way to measure how the chains are interaction, how they pack, right? If it's not a fleece, it's not random, and you get like you're going to have charges between these things, and you get a peak in this. But the same thing happens. It still diminishes, and there's still an interaction. But there's a fixed value of size. So you'd see a peak here that would be like this, the spacing, like in the shirt, they're woven fibers. So you would see the fibers, they're regularly spaced. So there would be a peak in the scattering, like a diffraction peak. Right. So, but at the lowest Q, which is infinite size, that's the thermodynamic limit. It still behaves like this. It still diminishes, and that you can still get that interaction enthalpy in the crystal from that 0Q limit of the thing. So it's kind of like the two systems. This is called mean field when you have this random, and it's called specific interactions when you have a peak. So there's like two different kinds of things that can happen. I think that's kind of the limit of what can happen when you mix two things. I mean, those are the two theoretical limits. You could have something in between, but you can have random, which is mean field, and you can have specific, which gets a lot more complicated because you have to calculate all the energy interactions of everything in the whole system. So it becomes a lot. Mean field means you just say it's random. You can ignore that stuff. You just say there's one number, the thing that drives this down. So there's some, yeah.
Can the mass fractal dimension of a polymer be linked to its end-to-end distance and radius of gyration?
Well, it shouldn't. All right, so if you're going to measure it by looking at different size chain, I mean, in the case of scattering, you can measure it with one size chain. You can just get it off the scaling. So it's kind of looking at different sizes of the same chain. It's looking at like a piece here, then the whole piece. That way, it's kind of looking at the mass change in it. So it picks it off here. But generally, any other technique, you're going to look at different rates of gyration, different mass, and then see how the kind of the volume or the density changes with changing that mass. So that's a parameter that you're going to use to determine the fractal dimension. So they're related in that that's how you determine it. You're determining it by changing the size, measuring the mass and the size, the volume and the volume and the mass. Then you're going to determine the mass fractal dimension from that. Right. So in general, in polymers, because the fractal dimension was invented by Mandelbrot, more or less, like in 1968 or something. And he wrote a book, and I think he won a Nobel Prize, but it wasn't about polymers. It was more about these kind of clusters, like dust bunny things. He was in New York at IBM, like IBM lab, like north of New York City. But anyway, so yeah, he won the Nobel Prize for that, I think. Just defining this kind of dimensional analysis, but he not a polymer person. But then Fleury was in the 60s, before that. So he didn't know about fractal dimension. He didn't know about that this is a two-dimensional object, things like that. So he just called this 1/2 factor here nu. So you'll see, so it's a scaling coefficient. So it's a little bit, anyway, so this, like he'll say,
You have to switch.
oh, sorry. All right, so you'll see, like, if you look at Fleury's book, he's got R goes with N to the nu L. So nu is one by this mass fractal dimension. So there's a lot more insight if you talk about it in terms of a dimension, because you can say, you can get a better idea, like you have a disk spinning around in space, that's the same density as this random walk coil of a linear thing. Right, so it means that, but obviously there's some difference, right, between the two. So what's the difference? You have that thing and you have a disk, like those are pretty good. So this would be a beta sheet, and this is a misfolded protein.
So they call these natively, some of these aren't like whipping up the eggs, some of these are natively misfolded. That's a big area of research now. Because people have studied, all right, so they've literally built synchrotrons, like $500 million machines to study natively folded proteins, because there's a ton of money in it. Like small changes in that collapsed structure can lead to like curing a disease, not curing a disease. And that, so there's like many biophysicists and biochemists that are like producing these proteins with slight changes to get some kind of shape that they know that they need to do something, right? So they've kind of nailed that down. So you can go to the protein data bank and you can get the structure of like, well, probably like at least hundreds of thousands of different proteins, right? Then they find out about like 15, 20 years ago that like, well, 30% of proteins that are active in your body aren't folded. They're called natively unfolded proteins. So all of a sudden that's like, oh, there's going to be a lot of money in that research, right? So basically, most of those are like, if you have a membrane, or say in the folding process to make that small object, you have to have this other proteins that aid in it. They're called chaperone proteins, and they're misfolded. So they will guide, like, so the ribosome, it's going to produce that protein that you're going to make insulin with. But on the path to go from the ribosome to the insulin, something has to happen to make it fold up, right? So there's these chaperone proteins that guide that, right? So basically, that's like where all the action is. In other words, if that mechanism gets screwed up, then you die, you know? So basically, figuring out how that works is going to be leading to this natively misfolded protein thing. So in other words, boatloads of money are going to come in, and you can't study it with a synchrotron because they aren't these fixed little cube things, whatever you want, whatever shape, right? They aren't perfect shape. They're like wiggling around all the time, but they have active sites that make things happen. Anyway, so you want to be able to distinguish those two, right? So anyway, so one way to do that is you want to look at this, you say I'm going to put electric current across this thing, then I'm going to see like, well, what's the resistance? Say like, if I'm going to run a current through this wire and it's a Brownian walk, it doesn't touch. So basically the resistance of that, so there's going to be some distance, P minimum, it's going to be a minimum path distance. And then the size of the thing is still the same, R, right? So P and R. So you had N and R, and N was going to 1/2. P and R is also going to go to the 1/2. But if you run a current across the disk, right, then that's going to go to let's see. So it's not P to the 1/2. P to the 1/2 to R into the it's R to the 1/2. Right? P is going to go to R to the 1/2, R to the 1/2. But if you go across a disk, then that P is going to go to R to the 1. So in other words, it's a fractal scaling. You're taking the original object and saying, I'm going to make a short circuit path. In the case of a disk, it's a line. It's a straight line because it's solid in the plane. So it's just a straight line across for short circuit. And this, for the short circuit, you have to take that same winding path we had before. So this is another dimension. So you have another dimension. It's called the minimum dimension. And the minimum dimension for the equals the fractal dimension equals 2 for the polymer. The minimum dimension equals 1 for the disk. It doesn't equal 2. It doesn't equal the fractal dimension. So that means if you have these two numbers, then you can kind of say what it is. You can distinguish the spaghetti from the plate. Right. So some kind of way to do that. So anyway, that's kind of partly what I wanted to talk about today. But anyway, so it has to do with so fractal is only useful to get density. If you combine it with these other numbers, you can say what the thing actually is. That's where this is going. Yeah.
You say so they actually are you talking about its shape, or what do you mean by that?
I mean, you can distinguish between a beta sheet and an unfolded protein. quantitatively. So neither one of them is exactly something that, a data sheet you can draw, but the unfolded protein you can't really draw. So it's a way to talk about what it is. So it's beyond, it's kind of a little bit beyond human understanding. Like you have to quantify things that are like a cloud. And you have to say like you have all right, so in polyethylene, if you have one branch per 10,000, one long chain branch per 10,000 carbons, which can't analytically be measured really, the viscosity increases by 45 times, right? So you want to be able to quantify, and so it's basically a cloud. You're making this thing and you're producing hundreds of thousands of tons of it, right? And it's going out into the rivers and things, but basically it's around. But basically you kind of want to be able to predict the 45 time viscosity change, because it's the difference between blowing up the extruder and not blowing it up. So being able to put a number down that's quantitative that has an error bar on it is useful. Whether you can comprehend that or not is another story, but so you can run the factory, right? So anyway, that's kind of the idea. I mean, basically, it's the numbers that are going to help you distinguish between things that you couldn't distinguish. Like saying the density doesn't help, like if you want to know the topology. So this gives the topology of it. Yeah.
So what's the difference between the fractal dimension and the minimum?
They can be the same for a linear chain. Okay, so when you say a linear chain, what does it mean? It means it's a line, right? So in some form, this thing has to have a dimension of 1 because it's a line. So it's a crumpled line. So you have a sheet of paper and you crumple it up. It's still a 2-dimensional object in some form, right? So there's another dimension that's like the connectivity dimension of that, exactly what the thing is. Like if you have a coffee cup and you have a donut, there's something the same about them because they both have they're both a loop structure. If you follow through the mass, they're both like a loop. Somehow, if the donut was made out of clay, you could make a coffee cup from it. Put it that way. You know, if you were talented enough to do that. Or you could easier would be to take the coffee cup and make it into a donut without breaking it. You know, so basically there's a dimension, this connectivity dimension that tells you kind of something about the thing. It's not what the object is, but it's another feature, right? So, but it turns out only 2 of these do you need to know, because of the mass density is the product of this dimension and that dimension. It's like if this is linear and then it's a random walk, if you put electric current through it, then basically this times that gives me the density thing. So I can say the density is composed of what the thing is and how much I crumpled the sheet of paper. So if I start with a sheet of paper 2 and I crumple it, the fractal dimension, the density will go up because I'm packing it into a smaller space, right? And the amount that it's going up is governed by this minimum dimension, which is kind of the crumpling dimension. So I'm saying a disk is an uncrumpled thing and a coil is a total kind of a largely crumpled thing.
So in this case, we don't talk about a 3D kind of dimension of the polymer chain.
All these are 3D.
Because it's this and also random coil that you said it's a linear, it's going to be linear. I mean,
Yeah, the random coils, I mean, if you talk about the word is like it's a linear polymer, not a branched polymer, right? That doesn't mean it's a line. So what does it mean? Like it's a linear polymer. That's the expression you use. A chemist would say it's a linear polymer or it's a branched polymer.
yeah, I
Right?
know.
So what does that mean? If a dimension of the thing is 2 and it's a linear structure, there has to be something else that's saying that it's linear. What that something else is, if you take the contour length and stretch it out fully, then it's a line. So you can uncrumple it, and then what is it uncrumpled? I guess is what it comes down to. What dimension would it have uncrumpled? Does that make any sense?
So the 2D dimension is the most dimension that we see in the case of polymer chain, in the protein chain.
So if you want to know the density, you have the fractal dimension. It's just the density. It doesn't tell you what it is. The plate, the polymer coil have the same density if they're spun around in space. Like they can, in other words, if you want to know how much do I have to put in before they touch and clump up and be useless, like for a nanotube. So how many nanotubes can I put into my composite to get so usually
like you'll see in the cartoon, like I was just looking at the paper this morning, they showed cartoon. So they're putting in 20% nanotubes into a composite to make a membrane that can conduct electricity or something. Right, for osmosis for water, seawater, fresh water. So, I mean, you can make it like if you have a river come into the ocean, there's an osmotic pressure between the ocean and the river. You can use that to generate electricity if you have a membrane that's ion selective. I mean, people have talked about doing that. They built actually pilot plants for that in Norway, I think. If you calculate it, there isn't a lot of energy to get, you know, but basically this has been a dream of people for some time, you know, that you can just generate electricity, not with turbines, but just with osmotic pressure. If you're near the ocean, you have fresh water. It's going to go in the ocean anyway. On the path through, you can collect electricity from osmosis, you know, but anyway, so say you're going to use nanotubes because they conduct electricity. Oh, sorry. So you want to, I probably should use this paper we talked about this. So what fraction, like how much percent nanotubes do you want to add to your, I think they're using polybutylene, butylene, which is like carbon, something like that. I think it's 4 carbons, 4 methyl groups, something like that, polymer, right? So they're adding these together. I know like how much, so you know, the length of the nanotube is something like almost a micron, it's like 700 nanometer length. And you know the kind of the whatever the, well, even just the 700 nanometer, if I cube that, then I get a volume, right? And then I know the mass of that from the whatever, 700 nanometer times the whatever, you know the mass of the nanotube, you can calculate it somehow. So you're going to take the mass of the nanotube, you're going to divide it by that 700 cube times whatever the, right? And then you're going to end up with some concentration. That concentration is going to be like 0.0001. None. You can't put any in. No, if you want to go to about that number, so you're going to get like this kind of setup, right? Network of carbon nanotubes in it. But if you go above that almost nothing, then what you're going to get is just clumps of nanotubes, basically carbon, like just coal thrown into the thing. And that's not going to really even conduct. It'll just be a mess, right? So this is a problem with this kind of nano composites, you know. So you have to worry about this overlap concentration. That's going to be just the fractal dimension. The properties you get are coming from the C dimension, which is 1. That means it's a wire. You want to have electricity conducted through a wire, that's the shortest path, right? But you need to know, you also need to know the DF of this thing when you put it together, so that you can see how it's going to. In this case, so if it's a rod, then D min, DF, and C are all 1. So 1 times 1 is 1, right? So D min times C is 1. But you need to worry about how it's going to fit together. Yeah.
So DF, is that the fractal dimension?
Yeah, fractal dimensions and mass fractal dimension. There's also, like if you do microscopy, you get a surface fractal dimension,
Okay.
which is a separate number. So that's going to go from 2 to 3. The DF is limited from 1 to 3. Right. In other words, you can have a rod, you can have a 3D. In 3D space, you have 1 to 3. I mean, anytime you're going to use it, it's 1 to 3. That means everything else like C, D min also have kind of limits of 1 to 3, but C is actually going to have a limit of DF divided by D min. Like, in other words, if DF could be 3, so basically the limits of C and D min depend on what DF is and what the other one is. Any two of them decides the other because DF is C times D min. Right, so you only need 2 of them. Then
Okay. So I want to know if this is also applicable to polymer powders, polymer like material formation with polymer powder.
polymer powders.
Yeah.
Yeah, it's good. This is good for anything. If you want to know. Yeah, in other words, it could work for macroscopic fibers. It's the same thing. So you're going to spin coat. So when they make something like fleece, they have an extruder and it's shooting out, and then they just literally blast the fibers onto a conveyor belt. and they just pile up, like for diapers, they do this to make the fluff and things, right? So basically, in doing that, that's called spun-bound fibers. And then there's also, you can also have, you can anneal it and make the fibers like stick to each other. They melt and they stick together. So you can have it spun bound, I forget the other one, it's like when they glue, maybe spun bound is when they glue together, and the other kind is just not bonded. Like two ways to make a non-woven, right? So anyway, it's like a very fast process, like the stuff's going through it 100 miles an hour or something. And it's really rapid and very efficient to do, and you can make kind of nice things with it that actually will generate microplastics in the end, though, because they're gonna like be these really thin fibers. And if they're toxins, the disposal of it's a problem, like especially for fast fashion and things. So it's gonna be like, maybe people wear it twice and then toss it. And then that becomes, because it's such small fibers and things, there's problems with these technologies a little bit, but anyway, so this is all over the world though, like the spun bound fiber thing. Anyway, so if you do that, the interesting thing is if you do that, so it's two kinds, bound and unbound. The unbound one, if you look at the unbound one, it ends up having a fractal dimension of 1.67 or 5/3. Means it's closer to a rod. Like if it was a rod, it was a 1, a polymer is 2. So it's a little bit less than 2, right? That's the unbound. And the bound one, when you melt it, it turns out it has a fractal dimension of 2, just like a Gaussian coil, because the fibers are actually like literally passing through each other because they're glued together. So it's denser when you bind it. And the density that it reaches is the Gaussian density. Kind of odd. Just this kind of materials just like exactly like polymer coils. Things behave in the same way. And when it's avoiding itself, you get this 5/3 dimension, which is that's called the self-avoiding walk in polymers. You have a Gaussian walk and a self-avoiding walk, like two limiting cases and stuff. In both cases, C equals 1, because they're both, even though the Gaussian one processes itself. I mean, for a polymer chain, the Gaussian one's a theoretical thing and C is 1. So the bound fiber thing, I guess it's branched. So it isn't 1, but
Can see the fractal dimension tells how thin the material is.
Yeah,
Okay.
yeah. How dense it is a function of size, molecular size, or object size. In this case, fiber size. So it can be macroscopic. It could be trees. Trees you can analyze this way. Rivers. Could be geological dimensions. Probably you could do it with stars or something. I don't know. I mean, but basically, yeah, it's not size dependent. It's just a way to look at things. Like, how do you look at something that's? So it's not like metals or something. You just have a crystal and that's it. Like you have the crystal, that except for defects, and all the way to like the whatever object, the airplane engine blade you're making, that's the crystal all the way up. And then like if it's could be grains and things, basically it's the crystal structure is going to determine everything. This is different. It's like you're building this thing up. So it's going to be different. You're kind of controlling this, the overlap concentration is an important parameter to know about when you're processing the thing and making it. Like how is it going to actually be put together? So anyway, it's like fun to kind of look at too. I mean, you can look at trees and stuff and figure out the difference between a pine tree and a deciduous in terms of fractal dimension. I mean, if you want to. I mean, if you want to make a synthetic for a movie or something or video game, this might be a pathway to be able to simply describe, like, I want it to look like that. Like you could give it 2 numbers and that would tell you exactly what forest you're going to get. So there's uses of it, kind of odd uses, but it's a thing people do. But yeah, was there a question or?
Yeah, I have 2 questions. One of them is, what factor affects the shape of the Gaussian shape, and could temperature or external force affects the shape of the Gaussian shape?
Yeah, so the coil, yeah, if it's a Gaussian chain, there's no, it's a entropy driven chain, right? So it's kind of a random structure and it passes through itself, right? So there's no enthalpic interaction. Temperature is going to be governed by the enthalpic interactions between the things. And those are kind of mitigated with temperature. It's like if you have two things that approach each other and they repel, then you raise the temperature. Well, that temperature is going to be motion pushing them together. They're moving around, and then they come up against this wall as a charge repulsion. Well, if there's a higher temperature, then they get closer. They can approach closer. In that sense, like temperature and enthalpy are kind of linked together. They're fighting each other, right? So if it's totally random, which is Gaussian, there's no enthalpy, so there's no effect of temperature on it. So that means if you have the non-bounded fibers, then basically the processing condition isn't going to affect much the density of the fleece that you make. But if you have bounded fibers, then the bonding conditions are going to have a big effect on the fiber size in it. So it'll be like a denser fleece you make. So basically, temperature won't affect the Gaussian at all. Temperature affects the self-avoiding walk thing. The temperature comes into play when you have interactions, and that you're trying to overcome the interactions with the temperature and motion of things. If that makes any sense. What about what?
External force.
Yeah, well, yeah, external forces. So yeah, the other paper I've been looking at is on fiber stretching in extensional flow, which is like if you take two plates and stretch it apart and you have goo between it, like glue, and then you stretch it out and then the chains are getting stretched out, right? So that affects, that'll definitely affect the chain size. And the models are that it affects the chain size. So yeah, so the chain size will increase with tensile force. So what you have is like dF will drop to 1. So basically if you have, so if you, yeah. So if you think about it, you have a Gaussian chain, and you're gonna like pull it, right, with some force. So you have some size R. Well, then it's gonna pull that chain. But so if you can do this with like I don't know, a shoelace or a string or something, if you put it on the table and you pull it, right? So it'll pull that out. So what you'll see is that, well, this at some size scale, so the chain itself wants to be a coil, but you're pulling it to oppose that. The force is opposing that coilness of it, right? So basically, it'll remain a coil at some size scale, some screening size like that, and it'll straighten out on a larger size scale. Right? So this is where the coil decides, like it sets up a new size scale in order to accommodate the pulling on it. You have the size scale R, and then you still have a size scale R that's larger because you pulled on it and it got longer, but there's a new size scale that shows up, this kind of correlation size. Right, and that thing's determined on a balance between like KT and the force that you put in. So force times distance is energy, KT is energy. So this thing gives you this screening size. Like how big is that size? I mean, these are thermally determined. If it's a springy fleece, then that KT is like the spring constant times the distance or something that you pulled it. So, right, so basically, the energy would be the distance squared. So, yeah, distance squared. So basically, that'll be like the energy for the pulling of a springy fleece fiber. And then the force that you pull on it, and it would determine this of the size that shows up. It's kind of the diameter of the rod thing that you're making. Right. So in that case, this thing has two dimensions. Within these things, it's got dF equals 2. And if you go to a large scale, it's got dF equals 1. So if you could do scattering on that, so I by C,
versus Q log, you see, oh, it's one dimensional. You get a -1 slope, that would be the R, 1 over the R size. And then all of a sudden it would go to 2, and that would be 1 over the squiggly thing size. And then again, if it was fibers, it would go back to 1 when you got to the Kuhn. So in order to accommodate that you pulled on it, the dimension changed, yeah, but it only changed it. What it actually did, it accommodated it by introducing a new size scale. Right, so it's complicated. Anyway, we'll talk about that later, but that's like the simplest idea of what the French called a blob. So they call this thing here a blob. I don't know why they used an English name, or if that's like a translation of, I think they used the English word blob. It's like the French degens, you know, and the other French people. So anyway, so this is kind of so yeah, you can take something like this. So just throw some circles on the table. So it's 2-dimensional, right? Because it's on a sheet of paper. So the maximum dimension this could take is 2. If it was 3-dimensional, it would be 3, but because I put it on a paper, it's 2. So that means the DF has to be less than 2. So just count up how many circles I have, kind of give a rough idea where the size is. Divide the size by D, so it's a unitless number, and then just get the scaling dimension, R by D, and Z is how many beads there were, and I get DF. So DF's 1.36, less than 2, that's good. And it's bigger than 1, that's good too. So you know the limits are like 2 and 1 in this case, because it's on a sheet of paper. If it was 3D, it would be 3 and 1. So 1.36 seems pretty good. It's kind of linear-ish. They can find the minimum path through it. So just find, there's many minimum paths. So it should be an average of all of them, but I'm just taking 1. So it'd be like 1's here, 1's there, 1's there. So there's a bunch of minimum paths. You need to take kind of the weight average of those. So take that one. So you have that many beads as P, this minimum path. If you take P and R by D, you get this minimum dimension, which is close to a rod. Like 1 will be a rod, so it's a little bit squiggly rod. So I guess that's okay. And then you get this other thing, like you can invent some number S, which is a number that if I just took the topological points, like the endpoints and the branch points, and then I made a stick figure with that, and then I would have a mass of that stick figure. So I'm breaking this thing apart either into a minimum path or into the stick figure path. And then how does the scaling go then? So this C would be 1.28. So that tells you how branched it is. Or it's how would you say, like, how branched is this thing? That dimension gives you, from this number, you can calculate how many branches, the length of the branches. Basically those two things, like the average length of a branch, how many branches. And then, so that works, like DF times D-min times C gives you DF. Like it's a little bit bigger than 1, so it gives you DF's a little bit bigger than C. And then that gives you the whole picture of kind of what this thing is, more or less, from a viewpoint of just statistics. So if you want to, in other words, it doesn't exactly allow you to reconstruct it. I mean, you could kind of reconstruct some objects like that have these same numbers, and they would kind of all look the same. So you can kind of reconstruct it, but it's giving you on an average sense what the thing is, which is what you need to know if you want to know what's the strength of it, like what's the modulus, what's the conductivity through it. So all the properties you would measure of a nanoparticle on a large scale are average properties. They're not really,
What is Z representing?
C's the mass, like how many beads.
Oh,
That's just how many. So P, Z, and S are how many circles on the sheet of paper. Just count how many, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 would be P, right? This is 12. Right? And then count the others is like 20. There's Z is 27 total. If I make the stick figure, I get 22. Right? So you can kind of figure it out that way. Yeah.
How do you make the stick figure from connectivity from the original molecule?
I just took like the endpoints and the branch points, and I drew straight lines. And I filled those straight lines with circles of the same size of the thing. And I just counted how many.
Okay, and does it like lose 1 for each intersection?
I just added up how many are there. If you do that, so then I just did that, and I calculated the dimensions, and it turns out like exactly DF equals D min times C. So I didn't pre-do DF D min C, that just fell out of this. And it's just like a sketch, like a PowerPoint thing.
Oh, I see.
So,
You're just taking
yeah,
a straight line.
from,
from
I say
endpoint.
from that point to the branch, draw a
Yeah.
straight line. So it's a stick figure of this thing.
Yeah.
So it doesn't have the reality, but it would tell you like, I mean, it tells you what the kind of how the branching of the thing is,
Mhm.
the connectivity, how it's put together, just in terms of like how you'd have to, how many times you'd have to glue it to put it together type thing, you know?
Yeah.
And then this thing's telling you like conductivity through it. Those two things will give you the density. So in other words, density is made up of how squiggly or crumpled it is and how many times you glued it. Right, so it's kind of, what it does is give you a different framework to look at things that are, you would have no metrics to measure things like this. Like you have a dust bunny in the floor, you want to kind of describe it. Oh, it's a dust bunny, you know, like there's nothing to quantitatively you can talk about it.
Yeah.
So this gives you a framework to get quantitative numbers to talk about things that aren't, they're not bricks, you know. So and then this also gives you the advantage to say like, how much would I have to put in if I wanted not to clump the stuff up? You know, or how much dryer stuff would fill up the tube going out so the dryer doesn't work anymore. I don't know if that ever happened to you guys, but this is my wife screaming at me, you know, clean out the stupid tube, you know, it's not working. Basically, when you run a dryer, and if you have those accordion tubes, the stuff just clogs. And this is definitely has to do with this kind of dimensional analysis of the fluff that's coming from your clothes, which is microplastic, by the way. So I mean, it's like you're just producing it whenever you dry it. So don't dry your clothes. Or hang them on the line is much better, I guess, for this whole situation. But anyway, I guess the ideal thing is never wash your clothes. So, or don't buy clothes even at all. So just whatever. Anyway, there are no solutions probably. This is a picture of kind of that thing about the non-wovens, you know. So from that, like from that in the non-wovens, like in diapers, you're really interested in how much like urine it absorbs. You can tell that from this analysis. Like you can predict the behavior of something like a diaper. Anyway, so yeah, it's a good time to break actually. So I can do next time I'll do a paper. Maybe I'll do this if this paper looks okay. I just glanced at it, but the thing on carbon nanotube membranes seems to be kind of topical. And then I'll do that on Friday. I'll go through that paper. Right.
Again, I kind of came up with a question. So